Okay, so let's start. Hi, my name is Wolfgang. I'm a developer advocate with Actyx. And at Actyx, we built a platform to run decentralized applications on the edge. And we're currently focusing very much on the manufacturing industry. And the manufacturing industry has some interesting properties. So first, we'll talk about what is it that actually makes factories or developing software for factories. What makes that interesting? What makes factories special? And we'll see that it poses some really interesting challenges. And it sounds like, it requires some rethinking of things. Then I'll talk about what we did at Actyx to how we address these properties in our architecture and what we learned along the way. So where our assumptions were met, where our solutions did work, and what we learned that we could do better. So what makes factories special, actually? The one thing is that factories never sleep. So even small and medium factories operate in all around the clock in 3 shifts, and this is because if the machine is not running, then nothing is produced, and the factory doesn't make any money, but they're still paying for the machine. So to illustrate in what kind of timescales they often think is, that's an example from the far end of the spectrum, and it's the largest melting furnace in Europe. It's operated by ThyssenKrupp. And it was turned off for the first time in 2014, and it was built in 1983. And since 2014, it has not been turned off, and they are aiming for another period of continuous operation of 20 to 30 years. So, yeah, that's an extreme example, and it's heavy industry. But just to illustrate that these are vastly different timescales than what we were used to in typical software development projects, and how they, and the evolution in our space. Another thing is that unplanned downtime in factories is really expensive. It costs well over 100k euro for an unplanned hour across all industry sectors. The average is somewhere around 500,000, and in the automotive industry, it's even higher. So you don't want to introduce software there that makes production stop, because then you can probably count down the minutes until your company goes bankrupt. Another thing that is interesting about factories is that factories depend on really tight collaboration. So for a factory to actually make a thing, it needs to be given that a person operating a machine and the data that needs to be on the machine, the program that drives the machine, and some material must come together at the right place at the right point in time. And these processes that happen during production, so these microprocesses, they are very collaborative, and they also happen in very close spatial proximity. So you can't introduce software there that creates additional friction. If you communicate from the hardware device to hardware device, then there may not be any friction. So it does not, you may not make it slower, even if it's only perceived slowness for the user that's using the program, your program. And the cost for this is that factories really need to optimize. They often operate at a pretty slim profit margin. And if you introduce UX where people are looking at spinners or progress bars, then it doesn't really matter whether it makes a dent in the overall process runtime or in the throughput, just because the people who are working on the shop floor are very sensitive to these things. They would just not adopt your software. They will just be hesitant. So you have to do something to explain that, or obviously to make no spinners appear, to make it really fast. And as Tyler Jewell wrote in his developer landscape in the article about latency optimized development, is that the lowest latency experiences are those where computation and data are co-located with the users. And incidentally, that's exactly what we have on the shop floor quite naturally. Also, factories don't really specialize in building software. They often do have, even especially smaller factories, they have an IT department, but these are the guys that keep the printers running and make the mail service receive mails. And also care about the network infrastructure, but these are not people you discuss software with. So you really need to talk to your users yourself, I guess, and you really have to take care of a lot of things during development yourself. You see that this image looks pretty kludgy, and this is because I just originally said arcade, and I cropped out some lines and characters and moved them around. And yeah, well, that's also an analogy of how IT departments in factories are sometimes run. So where does it leave us? This seems like it is hard to build factory software, and it actually is, and especially when coming from a cloud software as a service mindset, it really takes some adjusting. But if you squint hard enough, or if you squint just right, then it's actually not so different from a microservice environment. You also have largely independent components that need to communicate in an asynchronous fashion. You also want to optimize for throughput. You want to handle failing components gracefully. And in factories, all these concerns are just amplified in close spatial proximity. And currently, we see two approaches dealing with that. One thing is to push cloud tooling and infrastructure further out to the edge. Examples for that are, in the simplest case, just CDNs, or something like AWS Outposts, or cluster federation or cluster spanning on-prem hardware and hardware in the cloud. But we took the opposite approach because we thought, okay, the software, the processes happen locally, naturally. And we already have co-location of data, compute, and user. So there is someone operating a machine. The machine has an IPC. The operator perhaps has a smartphone or tablet or some device. And the data also is already near the machine, or in the vicinity of the machine, or on the device of the operator. So this is what we call local first cooperation. There is some more to it, but well, you can read up on this, and I'll put some interesting links in the chat after the talk. Okay, so what did we do to address these concerns? The first thing that we built is a distributed event log. We also thought about implementing it using CRDT, so implementing data replication between several edge devices using CRDTs. But as factories really often have an auditability requirement, so for security issues or warranty cases, you really need to trace back every step that happened. So that's quite a natural fit for an event log. So traceability for orders and audit facilities. So that was a natural fit. And also it gives us another means of thinking about our domain. So domain events, I think, are a great tool for modeling processes. And it's really nice to talk about domain events with your user when designing the software. So that was more suitable for us. Now, when we start with some nodes, I have 6 nodes here, and I colored 3 of them just to be able to distinguish between them. And now the nodes start emitting events and record them locally. So facts that are happening on the shop floor and are somehow entered into device, or just like retrieved over sensors, are emitted and recorded on each device separately. Now, for the devices to communicate, these events somehow must get to the other devices so they can react on them. And this is where we built a peer-to-peer network, a peer-to-peer mesh network. So these nodes discover them, the other nodes on the local network, and they form a swarm. This can be fully meshed or partially meshed. And then they start sending events back and forth. And this can this can happen either in a direct fashion, as you see between the orange and the yellow node, or indirectly, as you see, like transient in a transient fashion, like the yellow node and the blue node. So now they have all the events, but as you are probably very much aware of, is time in distributed systems is not so linear as we would like it to be. So we need to do something about that. Also, we're not only interested in single events as they happen, but we want to make some sense out of them. So typically what we call a projection in event sourcing. So we want to aggregate all our events into some kind of state. And as you see here in this example, we're just counting the events that were emitted from each node. You see the first state we computed says two orange events and one yellow event, and it goes to 3, 2 and 5, 3. But you also see that the blue events are not in there. This could be due to a network partition, because the node on which we're computing the state or on which we're observing these events currently cannot see the blue node or has had no chance to receive the events from the blue node. And now what happens if the network partition is healed is that we actually are able to sort the events that are coming in a global chronological order by virtue of logical clocks. We're using Lamport clock here. So each event has its Lamport timestamp, and then we can sort them in a global chronological order. And if we observe the state after the blue events got in, then we also have the blue, the number of the blue events that were emitted. And what happens then is that, or the end of this is that each node has all the devices and all the events, and all the events are actually in the same order. So what we can do now is we can compute the state in a deterministic fashion on each node, regardless whether it emitted the events. Just if it has received all the events, then it's actually our state computation is eventually consistent. And this is part of the local twin programming model. So if we have the state computation and we just deploy the logic that runs this state computation, this projection, if we just deploy this on each node, and the system gives us the guarantee that we reach the same state after computing the same events, then we have an eventual consistent system throughout the swarm. We have some more details on that, and if you're interested, just ping me afterwards and I'll send out some links. And the last thing that we built is the Actyx query language, AQL. So to make it easier to make sense of the event stream, we didn't want always to implement a new projection all of the time. So if you just want to, especially during debugging or during development, you don't want to create a state computation a projection that you just throw away afterwards. You want to query your event stream. And this is what AQL allows you to. You see that on the left, you see the raw event stream. It contains data from, 3 machines, I think, and it has this value changed event. And sometimes it changes the speed of the machine, some motor that's running in there, and sometimes it changes the temperature that is measured inside the machine. And if we look at the query here, we see that we select from machine. This is what we see in the tags. We select events that are tagged with machine and that come from the ID with those Actyx sample machine, and that happened between those 2 dates. And then we filter out the events that are mock machine 2. So we're only interested in machine 1 and 3. And then we have this case statement, which allows us to select something from the payload, which is hidden in the underscore. And then we put it into a new JSON object. And you see the result on the bottom right. So we have the speed and temperature for the machines 1 and 3. So that's a nice way to make sense of your event stream. And it's much more convenient than to write a new projection. So what did we learn from that? I'm actually faster than I wanted to be. So perhaps I forgot a lot of things. I'm drinking a sip of tea now. Actually tea, because it's even in here. Okay, what did we learn from it? One thing is that events really mirror the business domain inherently. So it's a really, really nice tool to discuss the process with your domain experts. And probably, I mean, that's probably the case why it has a lot of traction in the domain-driven design community. Once the hard problem is ordering the events in a globally consistent way, but computing state from the events is actually just a reducer. So you have the new state, you receive the new state by applying the next event to the previous state, and you do this over and over again. And if you get to a point where you have these time travel requirements, so older events are coming in, then you can just rebind the state up until the point before the first new event comes in, and then you just rerun the state computation. So as we saw, this worked really nice for fine-grained, for these coarse-grained business processes, something like an order comes in and then material is provisioned, and then the production step happens and the next step, and then the product is done and is taken to another place and packaged up and sent away. So these are processes that are great for that approach, and you can read the event log and actually see what happens pretty easily. But we also have another type of workflows which are much more fine-grained, which are technical workflows that happen especially when two machines communicate. So an example for that would be a robot wants to put something into a machine. So for example, it's like, hey, I have something, let's say I have some material, and the machine recognizes, okay, someone has material for me, I'd open the door. And the robot says, I see you have opened the door, I'll start putting in my thing now. And the machine says, okay, I'll keep the door open. And the robot says, okay, I'm finished putting it in, you can close the door. And then the machine says, okay, I acknowledge, I can close the door now, and so on and so forth. So these fine-grained protocols for machine-to-machine interaction create a lot of noise in the event log. So you probably want to have two separate topics for that. Another thing that is not special to our implementation is schema evolution, and along with an immutable event log. So you can, it's hard to change events afterwards. So you cannot change events afterwards, and there are several patterns to deal with that. A great overview is the book that Greg Young wrote. I think it's called Read Versioning in Event-Sourced Systems. It's on LeanPub. I don't know whether it was ever fully finished, but it's really good. So it's also free to read. Yeah, the other thing is that we saw you really need a reactive mindset. So you need to let go of this request response or command thinking. So it's not like the robot tells the machine to open the door, but the machine recognizes that something happened and decides for itself to react on that and to open the door because material is available. So that's something that is really, really helpful there. We also learned a lot about operations on the edge. We're really used to building software in the cloud and to just push to our repo, and it deploys all of our services, and that's really nice. And all our servers have great connectivity. Yeah, that's not the case when you deploy to edge devices on the factory. They may be offline. The Wi-Fi may be flaky. You just need you just need specialized tooling for that. And we have fleet management software, and we have looked at some of them. Some of them are really, really good, and some very commonly used fleet management suites are not really, really good, but rather not so good. So you need, it's not that you need the tooling that you get from typical cloud vendors. You need something like that when deploying and operating and maintaining on the edge as well. And the market there just not as mature as it is in cloud tooling. And you really want to build in observability, like sending out metrics, sending out logs. And for that, cloud systems are a really good complement, because you want to have the logs in one place. You want to be able to analyze the metrics from one database. So you want just each device to push that out to a central location. But the important difference is that reading logs and analyzing metrics is not mission critical for the business process, while all the local communication, so the actual business events that go back and forth between the different edge devices, are mission critical, and so they are able to run with much lower latency. But if you get your logs a little bit later, well, that's not so bad in most of the cases. Yeah, we also thought about designing for failure, and saw that the physical world is a great tool for consistency, because the physical world is consistent. That's physics. So if you are able to include sensor data in your decision making on the local nodes, then you're able to detect states that are invalid. So if the system says like the door is open, but the sensor sees the door is closed, then you clearly have an inconsistent state in your software, and you can react on that. That also works nicely with the let it crash pattern, so you then just try again, but not in all cases, because the physical world is not eventually consistent and things can break. So, and perhaps like compensating transaction for a robot that moved through a closed door are, well, prohibitively slow and expensive probably. You don't want that. And just due to the case that you have a decentralized system, that really forces you to think about a lot of edge cases. So what happens if you have a network partition here in that scenario? What could happen if this event arrives late? So this is really something that we still need to work on, to provide high-level APIs that kind of hide some of the things away, but sometimes it's just not possible. Sometimes it's just something you have to deal with. And the last point about user experience is that since you have these, if you include sensor data and invalid state detection in your application, then it's really, then you can provide great user feedback, but you still have to think about these cases and still build it. And that can be a lot of work, but it's obviously possible, and you can do great things about that. So you can like just this fail early, and you can provide very snappy feedback, even if something does not happen as fast as it should. And we're talking about very low latency, because it's just like between two data goes back and forth between two devices on the local network. And what did we learn about our assumptions? Well, one thing was what we also saw often, that Wi-Fi on the shop floor is often flaky. So if the machines are wired, and mostly that's fine, at least that's what operation tells us, to say like, there's a network cable plugged into the machine, how can it be offline? And sometimes they still are, but people seem to trust them. Also for the Wi-Fi, I've seen cases where someone put a pallet with metal rods in front of a access point, and obviously this changed Wi-Fi coverage, but it seems to be good enough. So people are not really suffering from bad network coverage on the floor. On the other hand, the processes that run in a digital fashion, like on the shop floor, these are mostly systems that only observe what happens. So they're doing analytics, they're doing like progress tracking and measuring utilization of machines, but it's not so common yet to actually control the process or to orchestrate a larger piece of process that spans multiple machines in a digital fashion. This is where these SCADA systems are typically used for, but that's not as common as we thought, and we think that it's emerging, but it's emerging less fast than we expected. As I said, these coarse-grained business processes are really a great, independent of whether you build it in a decentralized fashion or using this event. recording what happens on the shop floor in a factory is just a great fit for an event log. And the last thing that we saw is that we're working a lot with third-party developers who are building tools on our platform, is that they really face a steep learning curve, and that we probably need some higher level APIs there still. Because we're building, if you build UI applications or headless applications, you typically build them mostly in TypeScript, and if they have a UI with React. And so you have this modern web stack that you need to learn. You need to be aware of event sourcing. You need to be aware of the pitfalls of distributed or decentralized systems. So these are some things that not every developer and every consultancy that works for Factory has. And these are some things that we should make easier. And that's basically what I wanted to show. One last thing, I want to thank the great people who put up their awesome images on Unsplash so I could use them. So thanks to them. And now I think we have finished in time, and I will look at the questions now and stop sharing my screen. Okay, so do you have any questions? I see there are already some in there. So the first one from Ragnar, whether we use optimizations when recomputing state from your event log. Yes, we do. So actually we did in the first version, we supported snapshots, and you could configure how often a snapshot was taken, and you could compress them and stuff like that. So the typical snapshot pattern. So it did not have to go back in time so far to recompute everything from scratch. Of course, if you have computed a snapshot and then the node receives events that predate the snapshot, then you still have to recompute based on the snapshot that was taken before. The current version actually, I think, does not have snapshots in place right now, because retrieving events and recomputing them is really, really, really fast. So this is, you can have a look at Actyx Banyan. This is the implementation that's below that. That's a data structure that is made up of it's a very, a very shallow tree with a lot of leaves. So I don't know whether I said this correctly now, but have a look at Banyan. So, so that was from Ragnar. Samson or Vicenti, this is an interesting domain. Do you have a published case study of this for public reference? Yes, of course. You can go to actyx.com. I'll just put in the link. Yeah, I just put in the link. There are some case studies on the site. I'm sure you can dig them up, and if not, just be in touch and I'll find something out. Okay, Chris asked whether we construct simulations of these physical systems. We actually typically test that our projections were correctly when we put in some events. Then we just can assert the result of the state computation, and then it really doesn't matter where these events come from. We can simulate missing events and stuff like that, and we do this in our tests. But yeah, well, we also simulate failing nodes. So we have a library that spins up virtual nodes and uses them. It's based on Rust NetSim, I think, where we can simulate that. But with regards to automation, we typically see ourselves on a higher level than the actual automation. So the automation really provides some more coarse-grained functionalities, not like every single movement, and then we just trigger this by talking to the PLC then. I hope this answered the question. If not, get in touch after the talk. The link to the ebook is, yes, share it, and that's on LeanPub. It's really, really good. Yes, it's here. Okay, and I think with that we are at the end of the session, and if there are no further questions, then I'll leave now. Thank you very much for your time. If you have further questions, don't hesitate to get in touch either over Twitter. I'm 0x Cafe Babe on Twitter, and yeah, or I'll be around here in Hopin. I don't really know how this works, but yeah, be in touch if you have further questions. Thank you very much for attending. Take care. Bye.